we can more or less start, right? So we have today, we're on time. We have today Alois Castellano from Liege, with his PhD in CEA in France, and then moved to the group of Mathieu Straat, who's also a professor in our institute as a postdoc, and he will tell us everything about phonons, I guess. Please go ahead.
Exactly. So thank you for the introduction. So yeah, I will talk about phonons today. Because we developed really recently, like last year, a new way to see the phonons to approach the problem of describing vibrational properties in material. So then, this is really the summary of my talk. It's atom moving, we have some temperature, and our goal is to get some phonons, some vibrational with the vibrational frequencies and so on, that is able to describe how atoms vibrate in a system. Why we do this? It's very simple. If we say finite temperature, what we hear usually is that atoms are moving. That's what you learn when you are in high school, for example, that temperature is actually the motion of atoms. And this gives rise to a lot of properties that would be interesting for applications. For instance, the movement of atoms is a signature in spectroscopic method, like you can send some neutron sources on a material and you can extract the phonon spectra. It's really important for electron scattering, so the phonons will have a lot of effects on the mobility of electrons, changing, I don't know, for example, thermal conductivity, thermal transport due to electrons, but they will themselves contribute to the thermal transport. The phonons are really an important carrier of heat in insulators. And the standard way we approach, at least on the theoretical side, to explain the other vibration is through the harmonic approximation on its perturbation theory. We start with the bottom surface, so the potential energy of our system. We look close at a minima of it. From this, we obtain some phonons on their interaction. So phonons in the end are the displacement pattern associated with the minima in the end of this potential energy surface. And from this, we can extract a bunch of properties. So, like I said, spectra, some thermal transport, so also some thermodynamic properties like to compute phase diagram and things like this. What I will try to show here is that this method that we use usually is actually quite limited, and I want to show you how to get further than this. But first, why is it limited? So let's go back to the basics. So maybe it will bring back some memories from when you were a student. The harmonic approximation on its perturbation theory. What we do is that we have a Hamiltonian with a kinetic energy term and a potential term. It's some function of the position, and we want to extract some properties of this. This is normally too complicated to, if it's not one-dimensional, it's too complicated to compute, to get anything from this. So what we do is, we do what we can do usually. We make a Taylor expansion of the potential. We have the constant term, not really interesting for us. But the second term, which in the end is really the harmonic part of the potential, is a term that relates how the energy evolved when we have one atom displacing on another atom displacing through a quantity which are the interatomic force constants, which are second order derivative of the potential. Then we can continue our Taylor expansion. We get then interaction between three displacements. This will give us, this is related by the third order interatomic potential, which are third order derivative of the potential energy, and we can go on. And every time we add a new term, we get closer and closer to the true potential. The reason this approximation is interesting is because that's how we get the phonons. So with our Taylor expansion approximation, if we stay at the harmonic level, that's how we obtain the phonons. It's a quantization of lattice vibrations, and it's through the diagonalization of this interatomic force constant in Fourier space that we obtain the frequencies, the frequencies of the vibrations, and the eigenvectors, which is in the end the pattern of displacements that those vibrational states are describing. And the higher order terms are also very important because they bring in the anharmonic contribution, which are the phonon-phonons interactions. So, for example, here it's a dissociation where you have one phonon coming in, it interact by creating two other phonons. And with a perturbative treatment, this allows you to describe a lot of things in a system. The thing is that by doing all of this, we actually are assuming something that is not really respected in a real system. But for instance, usually we don't go very large in the expansion of the interior expansion of the potential energy. And we are assuming in the end, because of this, that we have small displacement. And if here it's really some molecular dynamics, so it's really a modelization of what is happening in some system, which is Li3ClO. At room temperature, I'm not going to crazy high temperature. It's not small displacement. We are very on a large, compared to the equilibrium positions of the system, it's large displacement. So already we can say that this first assumption is not really respected. Another way to see it is that we are assuming, in the end, by doing our evaluation, that this harmonic term is really dominant. It's what explains most of the dynamic in our system. But again, this is not really the case. This is something called the anharmonicity measure in silver bromide. Well, I won't go into detail to what is this quantity, but what it says, what this plot is actually saying, that more than 60% of the potential energy comes from things that are not harmonic. The harmonic term is not dominant in the potential energy. And since those are really the basic assumptions that we are making working with a harmonic approximation, it means that in the system, we won't have good results in the end from this approach. And this happens in all systems. Like this is something we computed recently. So we tried to get the Phonon spectra in helium at really low temperatures, 38 Kelvin, in its FCC phase. The green dots are neutron elastic scattering results. On the color plot behind it are results from the harmonic approximation in perturbation theory. And we get completely wrong prediction using perturbation theory. Then we have some system, like if I take strontium titanate, it's really known to have some imaginary mode, which has an interpretation. It's due to the fact that this phase is not stable at low temperature, but it's stable at high temperature. At the moment, if you heat up your strontium titanate to, for example, at room temperature, this phase is supposed to be stable, but from those imaginary modes, we cannot describe anything in this system. Or another example is that thermal conductivity in perturbation theory, at least if you scale to the three phonons interaction, is supposed to have a 1/T dependence with temperature. And in a lot of systems, this is not what we observe. We have some other exponent respect to the temperature. So we have to go beyond the harmonic approximation if we want to have a good description of what is happening. But the harmonic approximation is very useful because it has a lot of advantages. We have a quasi-particle picture. This is useful because we can start to make phonons interact with a lot of things. Like we can have phonons interacting with magnons, we can have phonons interacting with electrons, and we need this kind of approach to explain some phenomena. Like I was talking about electron mobility, we need them to have the electron phonons interaction in our system. So also we have some interpretation of phenomena. For instance, if we take free energy problems or thermodynamic properties, then we interpret a lot of things that are happening in solids as the quantum thermodynamics of a gas, or well, the thermodynamics of the quantum gas. And this is really useful to understand what we observe in materials. And another thing, but I won't go too deep into the detail in this presentation, but we have something which works at the quantum in the quantum limit, which is also something that we would want in something that's improved on the harmonic approximation. But then we have some drawbacks, which are actually all the three I present here are the same, is that it's approximate, which in another way it's perturbative, but which means that all the correction we make, we are assuming that everything is small, but I showed you that the anharmonicity part is not necessarily small. And in the end, because the underlying assumptions are not guaranteed. So the question we have to ask is, can we keep the advantages of the harmonic approximation while avoiding all those drawbacks? Yes, but for this, we have to use the right tools. So I will put myself in the mind of an experimentalist for some second. It's when we observe phonons, what are we doing? In the end, we have some perturbing source, like neutron, X-rays. We send this on a sample, on a system which will be in equilibrium. This is really important. And we observe the response. And then we have some spectra, which we can associate to the phonons. We don't have anything about the potential energy here. What we have is the response of the system in equilibrium to a perturbation, which means that the set of tools that we have to use, that phonons, are something really from linear response theory. Linear response theory, the building tools of it are correlation functions. So in our case, we are working in a solid, so we have displacement around some equilibrium positions. So what we want is the correlation function of our displacement. If you are more used in many-body theory, what I call correlation function, you would call Green's function in the many-body theory. Really important thing in this correlation function is what I put into parentheses, that we are making thermal average, because it's in our response theory, we are working in the system at equilibrium. We really have the effect of temperature in the equilibrium of a system. And of course, if we go to Fourier space, we can obtain everything, well, frequency results, and then the important quantity will become the dynamical susceptibility. And what we would like to do is we will construct a theory of lattice dynamics, not constructed on the potential energy, but constructed on the correlation functions. And this theory is called, that we developed recently, is called the mode coupling theory. So this is the moment where I will go with some more complicated details, but I will try to make it as simple as I can. So to construct it, we will use a formalism which is called the Morris-Zonzig projection formalism. So we want the displacement. This is our dynamical variable. This is the thing that allows us to describe how the system is, well, evolving. It's a dynamical thing. We will create a function which is a one displacement projection. You take a quantity, whatever you want, an observable, it could be the force, the velocity, and you put it in a space of one displacement. What I mean by this is that you have your quantity, which is observable, you apply your projection of it, and then this quantity is roughly roughly approximated by some constant time and displacement. It's a projection, like any projection that you would make mathematically. But of course, if we don't do this, you are missing some things that are not linear with respect to displacement. So we'll have another projection, which is the orthogonal projection, which takes everything which is not linear with respect to the displacement. This is our building blocks, the projection operators. And of course, then every operator can be written as the projected part on the orthogonal projection. When you do this, so we will do it on the force, first the projection part. We apply it on the force, we obtain something very important. We have some parentheses, so we have some equilibrium correlation, we have some thermal average coming out here, and we obtain that the projected part of the force is some constant times the displacement. On those constants, it's really important, it's a linear component of force, is the temperature-dependent generalization of the force constant. So we have again some force constants or some force constant, but instead of being derivative of the potential energy, it's something related to an equilibrium average. But like, as I said, this part is not complete. We are missing some parts in the description of the force. So let's do then the orthogonal projection. We apply it in the force. Then it means that this is the force minus the linear part. We do some complicated algebra, and we obtain something with a convolution of one term with the displacement plus something called the random force. All those random force is degrees of freedom beyond the one displacement. In the end, it's everything that we could not project on the force. It's called random force, even though it's actually not random. The randomness comes from the fact that we don't know what this is in the end. It's everything that is one displacement. We don't know it. On the other part is a memory kernel. It's called the memory kernel. It's the correlation function of all this random force. And what it describes is that it's the time-dependent friction. It's how the forces, all the displacement are dissipating energy into everything that is not one displacement. Then we get everything together, so the projected part and the orthogonal projected part. We obtain an equation for the force, which is like, as here, so with our linear component, memory kernel, and random force. We take an average, and we obtain this equation of motion. This is an equation of motion for correlation function, which is called the generalized Langevin equation. This equation is exact. There is no approximation in this equation for the moment. Also, it includes quantum effects, but like I said, I won't really talk about it. But this equation is exact. The frequency, the linear relation to the displacement, we know how to have it. All the complication in this equation is in the memory kernel. So now we will have to find how to get this memory kernel. If you remember one thing, that memory kernel is a correlation function of the random force, so everything which is not one displacement. So what we do is just we create new projection where we will project it on two displacements. So we will project it on two displacement. It gives something with a constant times two displacement. But this might not be enough, so we will project it again, this time on three displacements, and we'll have a new constant times three displacement. And we will repeat this as long as needed. Those constants will be the temperature-dependent generalization of our interturning force constants. When we do this, then we get back to the memory kernel, and we just have a new equation for memory kernel with the generalized interturning force constant times a 4-point correlation function. So in the end, we have a new basic quantity, a new building blocks for everything we want, which are the temperature-dependent second-order IFCs and the temperature-dependent third-order IFCs, with the second-order IFCs allowing us to, as with the harmonic approximation, to obtain some phonons, the phonon frequencies. But an important thing is that now we have the temperature dependence ingrained into it, which means that our phonons will naturally evolve with the temperature. There is no phonon-phonon interaction renormalizing everything. Everything is already ingrained at the level of the harmonic frequency of the frequency itself. On the second part is the temperature dependent, so higher order IFCs, which will create phonon-phonon interactions. But then again, it's not the same one as what we have in harmonic and perturbation theory. What we have here is something which also includes already intrinsically the effect of temperature. The interaction between phonons, it's not some quantities, a simple quantity which doesn't follow with temperature.
Can you say if at zero temperature this approach reduces to the original one, say? Or can you prove that exactly?
Yes, this reduces to the harmonic approximation evaluation at zero. Well, in the classical case, not in the quantum one, because you have 0-point motions that will change everything. But in the harmonic case, in the classical case, this reduces to the harmonic approximation.
Maybe you're going that way. I just wanted to know. There's never a free lunch, right? So what price do we now pay? What is it that you actually need to know to get all these things?
You need to have a sample of your system at equilibrium. Harmonic approximation, you take your system exact position, you move one atoms, you do it. If you do it theoretically, you do it numerically. Simple, between quotes. Here, you have to have actually your system exploring the exploring phase space. It's not it's perturbative at it's not perturbative. That's it. It's a linear response function. It's not perturbative anymore.
The temperature dependence is only in the phi, or is it also inside the kernel?
It's also inside the kernel.
It's in both.
Yeah.
And it's the independent, temperature dependent, in one and in the other.
They are related. Because in the end, in the memory kernel, it's related to the third order IFCs. And it's everything that is not here. So they will have a relation in the end. That's the. I mean, because yeah, it's everything that was not inside the frequency, so the second order interatomic force constant. So this, sorry, I will have to get back on my where else I went there. So yeah, this is all the building blocks that we need to construct anything. So I will just highlight here some really the difference in the end of conceptually between the harmonic and perturbation theory and the Mott-Cummings theory. Harmonic perturbation theory is we think always of it as in terms of phonons, which are quasi-particle, but it's a theory of the potential energy. For instance, phonons, we see it as eigenvalues of the harmonic part of an effective Hamiltonian. And then from those eigenvalues, we try to get the response to some quantities indirectly. It's really we go potential phonons, then the properties. And the frequency then is only related to one of many contributions to the potential energy. In actual dynamics, it's not. It's just one contribution against a lot of them. While the mode coupling theory, it's really a theory of the dynamical response. You are directly trying to obtain the response to the system to a perturbation. And I won't really have the time to go into detail, but here the frequency, it's actually an exact observable. It's the response of the system to a static perturbation. You have your system moving around, it's still in equilibrium. You have a static force disturbing it. This static force is related. The response to this force are the frequencies that we get with our phonon frequencies. I will not stay too long here because maybe it's mainly more for people doing DFT. What I would say is that we can do this with DFT. We just have to do, so as we said, no free lunch. We have to do some molecular dynamics, which is the expensive part, the complicated thing for us. We have something to do to extract the generalized internal force constant, and then we can compute some properties. If you have some question about it, you can ask me later. But now let's go to how to compute actually properties from anharmonic phonons, starting with a vibrational spectra. So let's get back to this idea. So it was our inspiration that we are perturbing our system with neutron X-rays. We observe the response, and this response, in our case, will be directly proportional to the dynamical susceptibility. So, if you recall, the quantity we were looking at until now was the correlation function. So, vibrational spectra with this approach is really transparent to obtain. We have, of course, a formula to get to this. It's some sort of Lorentzian where we have a frequency dependence into the line width, which we can compute from our generalized internal force constant, where we will have some temperature dependence over there. And of course, we have some real parts that contribute, not really important for us right now. And then we will, from this kind of thing, we can obtain from something which is very small anharmonicity, something which is quite peaked, very Lorentzian, really nicely behaved, where we have a quasi-particle description of really that holds on with a lifetime for the phonons. But we can also describe things more complicated. This is something that I got from an actual simulation where, and this is one phonons, I don't have multiple phonons inside of it, where we have some satellites appearing. Here it's really close to the main peak, so something will happen in the middle, but where we don't even have a quasi-particle working anymore. And this is some of the things that we can obtain with this approach. The first example on which we apply this formalism is on, like I already showed you, the harmonic perturbation theory of it is FCC helium at 38 Kelvin. So this system is really interesting because it has really strong harmonic effects. It's actually one of the systems that started in the 60s. A lot of approaches which were trying to go to the anharmonic approach. It's a quantum material. You cannot describe this with a classical approach. And we have some experimental data. We have some inelastic neutron spectra from the 70s, which are actually represented here are the green dots. And as I already showed you, if you do simply apply perturbation theory on top of this, you have a long description of the frequencies in the end. We really are not agreeing with the experimental results. While with the mode coupling theory, by including really intrinsically the temperature dependence of the phonons already from the base, we have a very good agreement with experimental things. So already this result is contenders that we were on that this temperature dependence is really something that will can help us bring more accuracy in our results. Another example is something that I actually did during my my PhD on an alloy, so a substitutional alloy, which is uranium molybdenum. It's an interesting alloy for the nuclear industry for as a fuel for reactors. And the thing with this system, so it's a substitutional alloy, so you have a BCC matrix with some atoms filled with uranium, the other one with molybdenum randomly. it's a really strong harmonic material. It's in the sense that the harmonic, we cannot even apply the harmonic approximation on this because we'll have some imaginary mode, because you have a lot of instability due to the uranium that is not BCC at low temperature. So it condensates, it's really far from BCC. So you can even do a harmonic approximation, and of course, like I already said, you have some disorder. But we applied the theory on this system, which is what we have at the color plot here over there. That's all theoretical results already applied with DFT on the mode coupling theory. On the red square, on red dot are experimental results from inelastic X-ray scattering from done at the SAF. Yeah, we have quite a good agreement on between the two. We really are describing both the main dispersion of the system, despite the large anharmonicity, but also the lifetime due the broadening of the frequencies due to the disorder. And actually, from this collaboration between theory and experiment, we were able to show that there is a lot of correlated disorders in the system, that we have randomly placed molybdenum atoms, but it's correlated. It's not entirely random on the BCC matrix. In the end, to give more examples, we can actually describe a lot of things, going from very simple system like silicon. It's really in the Phonon community, in the Phonon theoretical community, that's the first thing you try because it's the simplest one. Harmonic approximation works perfectly well, and for us it also works perfectly well. We have well-defined quasi-particle. But you can also describe something more complicated, like silver chloride. It's a system where you have not so high temperature, you start to have superionic transition. So silver starts to go liquid while chloride is still crystalline. It's quite interesting. But this shows on the Phonon spectrum by the fact that all the optical modes are really broad and it's really diffuse. You can same optical mode is a bit of a stretch over there. We can also describe things like Phonon satellites, like here in PBTE, where this is our theoretical result from mode coupling theory, where we can observe really at the gamma point that here we have a satellite coming here. And this satellite is actually something that has been observed from its neutron here. It's from neutron scattering that has been observed in 2014. And also a result that I got from the literature, which applies unknowingly, but which applies the mode coupling theory. Some very exotic stuff, like here in sodium bromides, we have the appearance of segments. So here, if we look at the experimental spectra, it's a system with 2 atoms in its cell. We would expect 6 branches in the phonon dispersion. And what we have is that over there, we have some branch that should not be here, which are just some excitation, extra excitations in the system. And we actually observe, we are able to reproduce this kind of things, which is really interesting because it allows to help interpret what is observed experimentally. I will go now to another kind of thing that could interest us. So it's something that is really recent. So the work I will present there is actually from an archive that was, it's on the archive since Monday to tell you how recent it is. I'm going on to describe how phonon transport heat in a system. So let's apply a gradient to a material. So we have a material, we apply a gradient of temperature into it. We have Fourier laws that applies. The gradient of temperature is proportional to the heat current that forms into our system, with the proportionality constant being the thermal conductivity. And again, from linear theory, we know that the thermal conductivity is related to the correction function of the heat current. But what is interesting for us is that these kind of things, we can also describe it in a mode coupling formalism, where we will have something that will make the phonon spectral function appear, so the main product of the mode coupling theory, with a lot of quantities that comes from our renormalized phonon, from our temperature dependent phonons, like the generalized group velocity, so the derivative of phonon frequency with respect to momentum. We have this, and we have this renormalized. We have the effect of temperature on this. The heat capacity per mode. We also have this per renormalized version of it to the effect of temperature, and of course, our phonon spectral function. Going quickly on all of this. So our thermal conductivity can be decomposed into two contributions. One which is a diagonal contribution. So we should describe how phonons transport through diffusion, like the phonon is going through the material and diffuse heat inside of it. And another part which is of diagonal part, which is describe how transport through tunneling between phonons.
Can I ask a question before you go on? Let's say the starting point for kappa, is this exact, or does it somehow, it looks like an expression that neglects vertex per ranking somehow, like you have a product of Green's functions and some occupation by that. So is it exact, or?
No, we have some approximation coming here. Like this is something where we neglect the effect of, in particular, of high order heat currents. So here it's really the heat current due to one phonon. That we are, well, two phonons because it's a correlation function, but the heat current itself has only one phonon inside of it. And also here I'm not writing what is happening for collective effects. So thing where phonons actually transport collectively the heat, which is something which is described with the Boltzmann equation. I didn't went into the description because it's would take some time to go into the derivation of this, and I want just to give a picture of the thing. Sure. So, but this is an approximation. Here it's really an approximation of the heat transport through the phone. But yeah,
it's good.
So yeah, we have a diffusing contribution on the contribution which is due to tunneling between phonons. So or interference, where one phonon doesn't transfer its energy to another one by interfering with it. Well, let's apply this kind of theory to a system. So I showed you a lot of during this presentation this. So I will go back to this one, which is Alois, which showed allows me to show the importance of renormalizing by phonons. So I really also show you this one where we have some where we have the phonon, the importance of the phonon renormalizations with temperature, an important renormalization of phonons with temperature. And of course, I computed the thermal conductivity in this system. And when we have the harmonic contribution, which is what I have here, this is what you have, so only at the perturbative level. And when you go through a mode coupling formalism, you have also a strong renormalization of the heat current. And this contribution is way closer to what you observe from if you go to more exact but more expensive, more expensive method. But here we have something where we have a strongly anharmonic system where we have some lot of renormalization of our phonons. But I can also show you what happens for a system where this renormalization is not so big. So we studied recently iron rhodium, which is a system with a phase transition in the middle. So at low temperature, it's antiferromagnetic. On the iron are aligned antiferromagnetically, and if you go to 370 K approximately, at least experimentally, that's where the phase transition is observed. The system becomes ferromagnetic, not paramagnetic, but really it's ferromagnetic to antiferromagnetic to ferromagnetic. Well, we were interested in how the thermal conductivity evolves through this phase transition. So we computed the thermal conductivity in the system in both phases at the harmonic level with a perturbation theory. And what we observe here is that basically the system have the same thermal conductivity. So there is no difference between the two. Changing the spin texture in the system doesn't change anything. When we introduce the mode coupling, when we introduce the temperature directly independence in the description of the system, we have something quite interesting to see, that the ferromagnetic phase, the high temperature phase, is not really doesn't really need to have this temperature evolution included inside of it. But the antiferromagnetic state that I represent blue is actually pretty impacted by the temperature dependence of its phonons. So in the end, even if we don't have a strong atomosity in the system, we have a qualitative change already of the results that we have. We have the fact that changing including the temperature dependence into our description changes the way we see the evolution of thermal conductivity at the phase transition. And we can
understand why? Why does it impact further the antiferro?
Yes.
Yeah,
This is-
sorry.
So the main reason is that if you stay at the harmonic level, you have only one mode with an instability. It's a very small instability, which is just related to one mode. It's something. It's a B2 structure, and it's quite. You see this kind of instability quite often in this kind of systems. And all the renormalization of the semiconductivity comes from the fact that with temperature, this phonon mode hardens. So in the end, the phonons of frequency get a higher frequency quite quick for this mode. And this is the reason why only the antiferromatic model, the antiferromatic phase, is impacted by the phase transition. And of course, we can explore a lot of other things. So these are results I obtained from the temperature, like thermal conductivity in uranium dioxide, where they show the importance of the renormalization of the phonons, like I showed you on iron rhodium. But actually, the renormalization of the phonon-phonons interactions themselves is also really important. So what to show this, they computed the phonons perturbative theory. This is the black curve. Then they just renormalize the phonons, but keep the interaction between phonons at the perturbative level. And they have a drop in thermal conductivity, which is really important. If you then include the temperature dependence in the phonon-phonons interaction, you renormalize also the thermal conductivity, and with something which is really close to experiments, which is something where it was really puzzling for the actinide community to explain why the thermal conductivity in this system. Also, here it's another result also from the lecture. Again, it's strontium thalate. So if you remember, strontium thalate has some imaginary mode in the harmonic approximation, which means that you cannot apply it on strontium thalate. But if you use the mode coupling theory on this system, you actually reproduce experimental measurements, but also some exact molecular dynamic results, which are some results that are very complicated to obtain, very expensive theoretically. And lastly, for thermal conductivity again, we keep the interpretability. What are another results where in the end they have the thermal conductivity, they have the number they wanted to obtain, which is nice. But you are also able to get the frequency dependence of your thermal conductivity to understand why your system has this thermal conductivity, which is very important if you want, for example, to be able to tune this thermal conductivity or any properties in it. I will finish on the application of our method just to show quickly some range of applications. So I've been focusing here on the spectra on the thermal transport, but it can also apply to electron-phonon coupling. So for instance, trying to get all the renormalized phonons coupled with electrons to get, for example, the mobility. Here in this example, they actually apply the renormalized theory method on again on strontium thalate, so imaginary mode in the harmonic approximation. And they have what this picture showed, the FPG's perturbation theory on TDEP would be the renormalized theory that I showed you. It's that it changes a lot how phonons interact with electrons. And also here it would be unphysical to have imaginary mode interacting with electrons. Something also quite recent that we did is that with the theory, we can actually compute elastic properties. So again, in the iron rhodium system, we also studied the elastic properties of it by computing the elastic constants, which are in the end, the curve that we have here, on the temperature dependence of the elastic constant. And the elastic constant were also measured experimentally, and that the dot on the square that you have on this graph And you can see that for the C11, we have some very good reproduction of the elastic constant, and also on the evolution of it across the phase transition. With the other elastic constants are less. We have less agreement for the elastic constant or the other for the other elastic constants, but this is something which is quite often happening with DFT. We can also obtain some optical properties, like here is some work done by a PhD called José Batista in Liege, where we are studying the optical property in the end, here in particular the electric function in it, to show some hyperbolic properties. And also some work done on magnon-phonons coupling to show the evolution of the interaction parameter between the spin with temperature, with the effect of really of the phonons themselves. So I will stop here. So I will just start by thanking you for your attention. Just to give a summary of what I present you, it's a mode coupling theory. It's a theory of the dynamics of atoms, which works with the introduction of generalized temperature-dependent IFCs, which can be used to compute a lot of properties and improve a lot the results to compute the harmonic approximation, allows to understand what is happening experimentally. If you are someone doing some theoretical working with DFT, we have an implementation of it, and if you want to try it, don't hesitate to contact me. And I've also put the paper describing the theory over there. Again, thank you for your attention.
Thank you very much. Questions?
So I'd like to get back to the what you need. So I understand. Okay, basically this can take, as long as you can supply the correlation function or response in any way, then you can get all of this wonderful stuff out. What I'm wondering about now is how this works when, let's just call it extrapolation. Like, let's say you can only access up to one particular temperature or small temperature range. Can you from this now infer temperature behavior outside your window, or?
Well, you can always apply the equations. Usually it doesn't work that well, but it doesn't work that well in the same sense of the harmonic approximation, which means to give a simple example, so the silicon is a really harmonic material. Harmonic approximation works wonderfully in silicon. In this case, yes, it would work, but simply because the mode coupling theory goes back to the harmonic approximation, which works well for the system. If you go to a more complicated system, which like most of the system I presented here, I would expect it to completely fail. Actually tried it on something, it fails completely, because you need to actually have some information about what is happening if you want to describe what is happening.
It's maybe a comment. Thank you very much. Very nice work. If I couple a particle, a system, to a harmonic bath, a Duine, you get a spectral function, which is depending on omega. But if instead I couple to a truncated bath of harmonic oscillators, which is just the two-level systems, it happens that I will get a spectral function that depends on temperature. And it's very interesting because it's some tangent hyperbolic of h omega I over kBt, where h omega I is the frequency for each of the two-level systems bath, which means with the temperature I tune to each bath I'm coupling stronger or weaker. And I am wondering, because the Moritz-Vanni approach is analogous somehow to the Castellano, they were working at the same time. I wonder whether the two things could bear some similarity.
I think so, because, well, okay, here I'm rating a bit. Wait, that slide. Let's go back to the equation of motion that we create for the system. Well, here.
Yeah, there.
Where
your kernel will be temperature dependent.
This is yes, this is temperature dependent, and so this is called the general Langevin equation,
yes.
which is pretty something that is here to describe a lot of system interacting with the bath. A way to interpret this equation is to say that the phonons are harmonic system interacting in a bath made of all the other phonons. It's in the end, it's a
Yes.
self-consistent bath.
It's a two-level system coupled to.
But we have a bath. The memory kernel is a bath in the end. It's really the bath coupling
Yeah.
themselves,
Of
but
course.
it's so there is probably some similarity in this description.
And I have one more. So we have been looking at a generalized Langevin equation where now the friction is a fractional derivative. It's not so in the usual Langevin, friction is velocity, its first derivative with respect to time. We have been looking at an alpha derivative.
Okay.
So, and I wonder whether this could be applied anywhere in your model. Because what we see is that you connect the different states of matter. You start getting different kinds. So usually the Langevin, you go from ballistic into diffusive, but now here you get other regimes. You get a time glass with an emerging periodicity and so on. And I wonder whether one could get it here for phonons.
That's a good question.
It should be in the kernel, right? The kernel is
Yeah,
in general,
exactly.
so in principle it could.
Yeah.
Some purely depends on S in this case that
Exactly.
needs some strange derivative.
Yeah. And what would it correspond? It could be interesting to understand in terms
Yes.
of phonons.
Yeah, you said it's to go from ballistic to.
Yeah, so usually Langevin, you go from ballistic at short times, from ballistic into diffusive, linearity. But here you can get either a glass behavior, depending on the value of the derivative, where you saturate, or you could go into what we call the time glass. You start ballistic, and then you get plateaus, which are periodic in time. Or you can go to what is called this anomalous glass, the Gardner phase, which has still a linear asymptotic at high times, large times, but it still has plateaus also.
Okay, so I don't know, but this would be really interesting to look
Take
at.
a look.
Yeah, to find some system maybe was something like maybe it could be some system where very complicated spectral functions appear. And like for instance, this would be interesting to look at maybe the system with some extra dynamical bond appearing. This could be related to these kind of things.
Mm-hmm. Okay.
Yeah, but regarding this comment, I don't know if I'm not understanding properly this equation, but this is an equation for the correlation functions, not for the possibility. And it's not a stochastic equation. It's an integral differential equation. And the stochastic term was just introduced as an artifact to get this equation, like this Greenfield equation. But it's not here anymore. So that's one of the biggest differences with what we work with Christiane. Because here there's no stochastic term at all. So it was just introduced from the mode coping.
Yeah,
mechanism.
it's hidden inside the memory.
Yes, in the correlation.
In the end, if you were able to solve completely the memory kernel, maybe we would have a way to go back to because in the end they're related, and the relation between two is really important. It's the fluctuation dissipation theorem.
Yeah.
If you don't respect this, physically something wrong is happening. But for example,
somehow, because actually,
okay,
yeah, in those examples that Christiane is mentioning, there are cases in which, because you don't respect fluctuation dissipation, interesting anomalous behaviors appear.
Okay,
and you can get it from a bath out of equilibrium. So, I mean, you should respect it if you want to get the system in equilibrium and the bath in thermal equilibrium, but if not, you also get interesting things. And regimes.
Okay, so for example, if you start to drive a bit your system, or
like Partum,
okay,
No gradient.
Not a bit, the drive.
Go ahead, Raman.
Yeah, maybe some naive questions about possible applications of smart coupling theory. There's a large community working on net halide perovskites, because they seem to be quite important for photovoltaics and also electronics in general. And there, anharmonic theory seems to be quite important also. You have calculated anharmonicity in the Phonons. Can you also extend your theory to look for the interaction with carriers and the excitons? Because that seems to be exactly the third one. So I'm referring to the work of Omelia and David Egger. Say, I know.
So for the laser perovskite, this is definitely something where it's a good playground for this kind of for this approach. For all perovskite is really interesting to study with.
Because it's very soft material.
Yeah.
Large amplitude.
On the other phase transitions that are really interesting. What happens to spectral function at phase transition is really something that I'm actually really interested in. And to get to for the exciton coupling. So I went quickly on this. So I said that you can, for example, couple it with electrons. For example, that's one slide that I showed at the end. So technically, yes, you can have something where you couple like you would do with within the harmonic approximation. It's just that you would be in the end. Well, I will try to go back to the slide. So for example, what was done here, it's in the end we were saying, okay, all renormalized phonons behave like phonons, which is in the end close thing, and we use it as an input to compute the electron phonons coupling. So in the end, could be transparent to also couple it with excitons. It should be quite transparent. It's just that it would be perturbative. We would perturbatively compute the interaction between other quasi-particles. We are looking at how to compute interaction with other quasi-particles non-perturbatively. It's a work in progress. It's a starting because we have this problem of having access to the equilibrium to really have how the system behaves at the temperature, which seems to be which needs some work before being there.
As far as I understood their talks, they're also using DFT approximations to calculate this electron coupling in the anharmonic regime. So the she were able to do some work on it.
I mean, I'm not familiar with this work, so but maybe this is similar to what we do.
More questions? If not, then I think we should thank Alois again for my talk.